All right, so welcome everyone to the Kubernetes Masterclass 3. In today's class, we are going to talk about replication controllers, namespaces, and very importantly, service networking and a little bit of CNI. Now, why these topics are important is this is how you can achieve high availability, scalability in case of Kubernetes with for pods, that is with replication controllers. With namespaces is where you can achieve the isolation. And then with service networking is how you can connect one microservice with another. And also you can expose your services to the outside world using the same concept of service networking. But to understand service networking, we'll also dive deeper into the internals of it. And we'll also talk about a little bit of what the underlying technologies are involved. That includes the CNI. So let's get started with these topics. And let me start sharing my screen and we'll get started right away. Just to confirm, you're able to see my screen? All right, so I see Sanjeev, Tulsi, Cedric, Prakash, Aditi, and we may have people joining, and I'm just streaming it live, but I will not be interacting directly with YouTube because I can't handle both. So I'll be interacting with the folks who are registered and who are part of our, let's say the Zoom session. And people from the live stream can also join in our DevOps mini degree program to be part of our live class, interactive class here as well. So let's get started. What are we talking about here, right? So this is the setup that we have created last week. So I showed you how to set up a 3-node environment. All of this is running with one single Docker setup. So it can be your one laptop where you can set up a multi-node Kubernetes cluster like this very quickly with 5 minutes, and you don't need any additional resources. And this is possible because we are using a tool called as Kind. Kind allows you to set up a Kubernetes cluster inside Docker. And what you see here is a visualizer that is a third-party application, which is what I use to set up, to give you a visual idea about what your cluster looks like. And when you deploy things, when you roll out a new version, how actually rollouts happen, it's always good to see it visually. That's why we use this particular tool. It's all part of our documentation. Let's say we've talked about running pods as well. But if you run pods like we did last time, I showed you by creating pods and launching them and so on. So what happens with those is the moment you delete the pods, it's gone for good. Let me create a new one. This is a new setup. So I had to reset my environment. I've created it again. So let me just run a pod and whose name is vote and create it with an image like I did last time. So school of DevOps slash vote colon v1 with, let's say, and have to define replica. So basically, this actually creates a deployment now. It used to be a pod earlier, but let's find out. So kubectl get all, just gonna confirm. Since it is part of, is it deployment? Is it a pod? No, this is just a pod. So if you use create deployment, then it creates a deployment. That's fine. So this is good enough for us. So what I want to show you is if I delete the pod, what happens? So I'm logging into the same server and running kubectl get pods and delete one of this. That is the pod whose name is vote, this one. So what happens then is it's gone for good, right? So no pods are found. That's because of the typo though. So kubectl, it should be, that's the client, and it only shows me one. Let me launch it one more time. This is a new pod. You can see that it's running now. And if I delete it, it is gone for good. So how do I make it high available, scalable is where I need to launch it via something called the replica set. Secondly, I want to make sure that it is running in its own isolated environment for an entire project, because let's say the idea is if I want to deploy an application like this is a microservices application stack with 5 microservices: voting, Redis, worker, DB result. All of this is running as part of one project called as InstaVote. Now, you may have in your organization multiple such projects. So how do you differentiate between this particular project InstaVote versus everything else is where you need to start setting up some sort of an isolation. How do you provide the isolation is where we bring in the namespaces concept. So how do namespaces work? I'm going to quickly explain that to you, and then we will get started talking about replica sets also. So I'll create a namespace, isolated namespace, and deploy everything within that namespace. So what is this funda of namespaces, right? So namespaces give you this isolation. Let's say I want to deploy these 5-tier microservices on Kubernetes cluster. So Kubernetes cluster is made up of maybe 4 machines, or it could be 40. So essentially what I do is I will set up a cluster. So that's like my logical thing, logical entity, on top of which I deploy my applications. And underneath I can have 4 machines, 40 machine, 400 machine. That's the way I scale my environment, right? But ultimately you're looking at it as one logical thing or one logical entity, because we don't go to one particular machine when we run kubectl, get pods, get nodes, or any of these commands. We are talking to the cluster. We're looking at that cluster. So we're talking to the API server, which has a view of the entire cluster. Now you take that cluster and divide that into, or partition that into, different namespaces. For what reason? So that you can get that isolation. Isolation for what? So that, let's say your organization has thousands of pods across 20 different projects. Not every developer wants to see all those pods listed when they log in and start listing pods, right? So that would be too much to handle. There is a good chance that you may overstep somebody else's work. So what do we do instead is we set up some isolation so that we can define access control, we can provide different views, and that offers a logical separation for our environment, right? So that I'm looking at only one pod or one set of pods which are specific to a specific project. For example, yeah, I can list here pods from a specific namespace called as kube system. That is the control plane namespace. That gives me everything right from API server, controller manager, scheduler, HCD, networking, DNS, kube proxy, and so on, right? So you get logical separation and views. So if I switch to a different, uh, different namespace, I can see different set of pods and so on. And this also serves as a foundation for multi-tenancy, because based on the namespaces, scope to the namespaces, you can create RBAC rules, network policies, quotas, and it could be resource quota or object quota, either of that, right? So resource quota is about CPU memory. So you can say that this project takes 400 GB of RAM and 200 cores of CPU. In total, we are talking about, that's kind of a quota. And resource quota is how many deployments, how many volumes can be allocated to this particular namespace. So you can define all of that based on the namespaces. So namespace is a very important concept. How do you switch the namespace? I'll show you that quickly. So I have this command called as kubectl config get hyphen context. And you see the context here, which is made up of my username and cluster name. So if I switch the context when I switch the username, so I can connect to the same cluster as a different user with different authorization, or I can connect to a cluster, different cluster like prod, stage, dev. So that would be context switching. So you can switch the context, or you can just switch the namespace. I'm not switching the context. So when I use get set context command here, I'm only dealing with the namespaces. So I'm not switching the username nor the cluster. So I'll say I'm gonna use the same context. Within that context is my namespace. So I'm gonna say namespace can be anything. So the moment I switch the namespace to like kube system, for example, my view changes in the bottom. Yeah. And then if I use get context, it's going to tell me that I am now looking at kube system namespace. I'm working with that. I can go back to the default. When it was blank, it was mainly a default namespace. I'm back to the default. So which namespaces are there by default? You have default. That's where all your pods get created by default. Then you have kube system. Then you have a couple more. We don't generally use them mostly. You can add some ingress and all that in kube public also. Local path storage was created as part of the kind-based environment. So this is where we start creating a namespace. So this is what I'm talking about, right? Within one context, a context is a particular user connected to a particular cluster. Let's say this is my context. Within that context, I can have a different namespace. You can create different namespace for different projects, different environments. Mostly it is for different projects, right? So you can, that's up to you. That's just a logical separation. For this project called as InstaVote, we will create a new namespace.
Gaurav,
Yes.
can we share the namespace with the different users?
Yes, you can. You can provide access control based on the namespaces. That's part of what we call as RBAC policies, role-based access control. Let's say a developer is a role, and there could be multiple users which are mapped to that role. So you create a role saying developer, and then you have 20 developers. You can put them in one group, or individually you can provide access saying that this group or XYZ has developer access. And then based on that developer access, certain permissions are set, and you can restrict a person or a user or an application to a specific namespace. If you want to understand how that is done, there is a lab as part of our Kubernetes lab guide here. And that lab is somewhere here, creating users groups and authorization. So this is where I explain how the roles are created, what roles with an example. So there are three roles we create with particular namespace access or cluster access and so on, and read-only access for one user also. So for interns, it's read-only. For developers, it's a particular namespace. For ops, it's all cluster-wide. So you can define the role-based access very easily. That's why
Got
we
it.
want to have namespaces. All right, so let me create a namespace for this application stack called as InstaVote. This project, let's say this is our project InstaVote. It might have multiple applications. There could be multiple instances of each, so maybe 20 different pods. So that's fine. But I'm creating a namespace here using kubectl. Let me list the namespaces and then create one. Kubectl create a namespace, and then I'm gonna give it a name of the namespace. That's it. So that's gonna be InstaVote, and that namespace is being created. It doesn't mean I'm switched to it or I'm working with it, because if I use get context, I still have or connected to the default. And then I will use set hyphen context and then the namespace. And then I'll say instavote is my namespace. And it is switched. Now it is switched. Now I'm working exclusively in the InstaVote namespace. So whenever I run something, apply or whatever, by default, if I do not provide the namespace, it creates in the current namespace, which is InstaVote. Right now it's blank because we just created it, no resources inside. And now is the time we'll talk about how do we create the replica set, for what reason. And that's when we bring in high availability and scalability part of it. Why do we need replica set, replication controllers? And then we'll build on top of that with deployment. Ultimately, what you create is a deployment. So last week we talked about pods. We looked at how to create pods and how to launch them. Now, what happens with the pods is, if you just create the pods, what happens is, it if there is a problem with the pod or with the node, let's say you have a node with a problem, what happens in that case is all the pods running on that node are gone. By default, if you just run pods, that's what would happen, meaning your application may be down. So how do we make it high available and scalable is where you start watching for the X set of pods with a particular property, and that watcher is called as a replica set or a replication controller. It maintains the number of replicas. Replicas of what? We are talking about pods, because pod is the unit of deployment, pod is the unit of scaling in case of Kubernetes. So everything is with reference to the pods only, right? And that's what we are talking about. So the moment you add a replication controller, it starts watching for it, and then it basically, every time there is a problem with the node, it will just launch it on a different node and it will take care of it, because the job of a replication controller is twofold. One is it has to maintain the number of replicas, X number of replicas for a particular application. Secondly, it also, like it maintains the availability, it also maintains the scale. So you define how many, and it has to maintain those many. So availability, scalability, both it can maintain. And that's what replication controllers do. How does it do that is where we talk about labels and selectors, which is a very important concept. So when we created the pods last time, we added some labels. Generally, we ignore the labels, but in this case, the label concept of label is very, very important because your scalability, high availability, everything depends on those labels actually. So how do these labels work, right? So that's where we are talking about the context of in the context of replication controller. What happens is these labels are act like tags that the replication controller keeps on watching. So you label the pods with certain things, right? So we labeled it as application vote, uh, role front end, whatever, and then you have matching selectors that you write, and so labels will always keep on watching or selectors will always keep on watching for a particular set of labels. So, and based on that, you are filtering basically saying that these are the pods I want to watch. So a replication controller will watch for a pod with specific properties, like, oh, if you create a replication, and for every application, like every application here, you are going to create a replication controller. So replication controller for vote application, what will it do? It will watch or filter the pods which match this criteria. App should be Python, role should be vote, maybe version is v1. So it's up to you how many to match. It's up to you. It's not necessary that, oh, there are three labels, so my selector should have three also. It's not necessary. You can say that I don't care about version, but I care about app and environment, and I will match those properties, and whichever pod matches those properties, I will start watching for those. That's how this works. So the selector and labels are very important, and that's how replication controllers work. Replication controllers are part of deployment. So deployments also depend on that. So your high availability, scalability, versioning, rollouts, everything depends on labels. Secondly, services, load balancing. So if you don't label them properly, your services or load balancers won't work. You will not be able to kind of route the traffic to the services and so on. So basically, that is where you're gonna have a problem, right? So your labeling and selections criteria has to be properly set up. So your metadata is supremely important in case of Kubernetes. Always remember that, right? So that's how you create the replication controllers and replica sets. Now there are two things there: replication controller and replica set. What is the difference? Technically, a very simple difference is, with replication controller, you can only do, oh, this and that and that. So you can only match by using ANDing, saying that, oh, if this is a pod, I can match app should be vote, Python role should be vote, and version is v1, or app and role, that's all, right? But what happens with, if you want a more sophisticated criteria, sometimes what you want to do is, oh, I want to watch anything which matches app Python and role vote, and version can be any of v1, v2, v3. So from v1 to v5, I don't mind. Or a version has to be set, I don't care exact value. So how do you provide this criteria is where you have to use set based selectors. So you can add that with replica set. That's probably why it is called as a replica set, and this is what we use today over replication controller. And it is not just because of this. Actually, what happens is, beyond replication controller, you also need to update the version. You have to go from version 1 to version 2. So you have to define some sort of a rollout strategy. That was not, replication controller is an old concept. When Kubernetes was created, there was only replication controller. And with that, you had to use a separate rolling update command line and feature and all that. You couldn't codify that. But with Replica set, when they launched it, they also created something called as a deployment, which gives you the update strategy. So when you take the replica set, add the update strategy, what you actually get is a deployment, which is completely codified or completely declarative code, versus replication controller does is not complete. It's an imperative approach when it comes to rolling out. That's not what is recommended in the world of Kubernetes, GitOps, and so on. The first principle of GitOps is you write everything 100% as code, right? With replication control, that's not possible. So we use a deployment. And if you look at the deployment, basically it is a replica set plus that strategy. Replica set will maintain the pod. So replica set will contain the pod spec also. And then this is how it looks like. So you take the replica set, You add the strategy. Strategy can be rolling update, recreate, whatever, and that gives you that automated deployment based on how you want to do it, and that gives you the deployment. And replica set contains the properties of a pod also. So you don't write the pods separately, you write it as part of the replica set. So how do you do that? I'm going to show you very quickly here. So if you have access to our courses, the Kubernetes course, you already have access to this lab guide, right? So you can find it from there and you will go through the namespaces, and then replica set is where you add the configuration. I'm going to show you how to write that configuration also. I'll take a pod spec and convert it into replica set also. So I'll go here, KTS code, and then I start using this directory called as projects, instavote, dev. So this is the way I organize my code. Projects can be multiple projects I'm working on, and then I have instavote as a project, and then it could be different environment. You can use hem or customize later to organize the environment specific code, but I you can use that as a reference basically. And then the convention that I use is the application name hyphen the object name. For example, the application is vote, object name is deployment. Vote Redis, vote vote ingress, vote HPA, and then Redis hyphen deployment, and DB hyphen deployment, and worker hyphen deployment. So I will create the file names accordingly. That's my convention. So in this case, I will write vote hyphen replica set. If you look at vote-replica set, which is part of the same code repository that you have already checked out last week, if you have completed the labs, that is for the pods, you are going to see the repository with the code which is completed. So I give you the code partially. So pod spec we have already seen, right? So when you look at this, what does it remind you of? Anything that clicks? What is this? This is a very specific thing. With replication controller, what is it that we are replicating? What replicas, whose replicas we are managing, right? So what are we replicating?
Pod replicas.
Exactly. So if you look at the pod spec that you might have written, and make sure that you're completing the labs on time, because otherwise you'll, kind of, it will be difficult to catch up later. So if you look at the pod spec, this is the pod spec. AKMS, API version kind, metadata spec. So you take all of this, remove A and K, because that API version and kind now is for replica set. And the job of the replica set is to manage the set of pods, right? X number of pods. So you define like how many replicas, whose replicas, pod replicas. So you have a template for the pod, and using that pod template, it's going to create those many replicas with the name slash hyphen slash some 4 or 5 characters randomizer, and to make it unique, and that's your replica. So this template is pod template. So from now onward, you will not write the pod spec separately. You'll write it as part of a template which goes as part of deployment, replica set, whatever. If I want to write replica set, how will I do that? The answer to that is Kubernetes API reference. There are a couple of different styles here that you can follow. I use the API reference, which is a one-page document. This is my favorite. Why? Because you can just browse to any of the resources and figure out the properties very quickly. And in this case, we are looking at replica set. So I'm going to go to the replica set and start writing the code on the left-hand side. What is the API version? API version is basically apps slash v1. Last time when I showed you pod, it was just v1. Why do we use app slash v1 is because replica set was added later. Okay. So if you look at kubectl API resources, you'll find that I have too small of a window here. Look at the third column, API version. For pod, it is v1, that's fine. But for a lot of other things. So if you use cron job, it has to be batch v1. If it is daemon set, it's apps v1. Deployment apps v1, right? Because it was part of a deployment apps v1. It was actually part of extensions v1, and then it became apps v1. So if you look at the replica set deployment and all of that, it becomes apps slash v1, right? So that's how it is. So that's the reason why we use apps v1 here. Kind is what? It's already given here. So I want you to just bookmark this part, the right-hand side document. That's the for one page API reference document. And why do I want that is basically this gives you everything that you need in order to work with Kubernetes. So if you want to work with Kubernetes, you understand the concept, then you come back to the API reference document and just start writing the spec from there onward, right? If you get into that habit, you're already on the way. That's the secret and the key to master Kubernetes. You're already on the way to master Kubernetes if you know this much. Now, let's look at the replica set spec. It has only four properties, so it is very simple. Minimum ready second. We can ignore this. This part is not necessary right now. So just think about three things: replica, selector, template. Template, you already see what it is on the left. Template is just the pod template, pod spec. So, right? So you can ignore this part and just focus on these two properties. We're going to add those here. Let me first write the kind here, and then I'll go to the writing the properties. So for replica set, the kind is replica set with R and S capital. Always remember that. So if you use something here, it's camel case, meaning first word will be small, second word will be like this is a camel case. First word is small, second word onward, first character is in cap. This is like a camel's hump, right? So that's why the camel case. This, on the other hand, is first character of every word will be. So if you use it as a value, it's always like this replica set with R and S capital. If you use it as a key, it's a camel case. So first word will be small letters. Metadata is typically the name of the application, and this is the spec that we are talking about. So we have to bother with only two things here, and this is the reason why I teach this way, step by step, so that because ultimately you use deployment. We could have jumped to deployment directly also. That's what people do mostly, right? The reason why we take this approach is this is a very step-by-step approach. Where we talked about pod. Now we've taken the pod and used it as a template. So we're just using one bite at a time is what we are eating, right? So that's always better to digest. Once you digest this, next time you come back, I'll show you deployment. It's very simple. Then it's just two things that you need to know about and you're done. And then you just understand how it works, roll out, roll back, and so on. So we focus on one thing and do it well. So we're going to talk about only
Gaurav,
two things here. Yes,
sorry.
go ahead.
Can we have this pod spec whatever we have written under template section, right? Can we have it in a different
Mhm.
YAML file and can't we refer it to here?
Good question. That's a very common question. The answer is no. You don't do that because everything. So you basically, this becomes a unit of deployment, replica set, or on top of that, we're going to convert into deployment. So you never need to, and you should not create a pod spec separately and reference it. It's not possible either. So pod spec is always part of a template. And on top of that, you basically have that template as part of a controller, like replica set here, or deployment, or stateful set, or daemon set. So you take any of these, you have the template. And even if you take two more batch controllers like cron and jobs, even there you have a template just with a different name. It's a job template there because it's run to completion, but otherwise it's a template. So template cannot be like you can't have a pod spec and say I'm referencing that pod spec. That's not possible. Okay. When it comes to writing the spec, right? So whatever you have as part of pod spec, that comes here. It can be as simple as just name and image, or it can be more properties. There could be 20 other properties out there. Now, leaving this template, there are only two properties we have to deal with, replicas and selectors. One is responsible for high availability. Second is responsible for availability. Sorry, scalability. So replicas is responsible for scale, like how many I define. I start with two. And selector defines or makes sure that those many two are available. That's the availability or monitoring part. So when we talked about availability and how it works, replication in general, it relies on labels and selector is what we talked about. And this selector is what we are writing right now. Since we are using replica set, we can also write a set-based selector. So that's what I'm going to show you here. What does that mean? What is a set-based selector? Let me take an example. I want to say that I want to select all the pods with app Python, role vote, and version can be anything. How do I write this? Or version can be any of v1, v2, v3. Let's start with that and then I'll change it. So selector is where you can have label selector, right? Which contains these properties, match expressions, match labels, match expressions, match labels. So when I just want to match label matching is just this basically. So I want to match anything with app Python and role vote. And the expression is where the set-based selector comes in. This is an object, this is an array. So you can have multiple expressions saying, I want to match these criteria, and each of these criteria has a key operator and values. An example that is key uh, operator values. Just write it this way, right? So list. The moment you see a list, you add a hyphen in YAML. This is the YAML syntax, and then you add basically key of whatever you're asked to. Any of these values which are necessary. In this case, I'll add all three for now. What is the key? Key is what I'm matching. A version. What are the set of values? This is a set of values. So I define the set. I can define it this way, or I can also define it this way. This is up to me. Both mean the same thing. What is the operator? There are four operators in the set, not in the set, or you can say exist or does not exist. In the set, as in when you define a set of values, v1, v2, v3, when you want to say that, oh, I want to match anything which falls under this and this has to match, and version can be any of v1, v2, v3. So that is what is defined here. Any of as in this set, v1, v2, v3, or you can say anything apart from this is not in. And then anything where we say just exist or does not exist, you can also define it that way. Operator can be exist or does not exist also, right? So in this case, I'm just saying with this set of values. So in case of exist or does not exist, you don't have to define the values. So it's just going to check whether the version exists or not. And then this has to match. So these two have to match. Version has to exist. I don't care about the version. So that's what I'm saying here. And that's all I need to define a replica set really. Okay. So on this side, I'm going to bring my visualizer. So this visualizer that I have, I want to bring it here so that you'll actually see how this works also, how the pods are replicated, launched, how they are run. So you'll see it on the right hand side. Okay. So now that I have it done, I can launch the replication controller, see what happens on the bottom. I'm going to watch for kubectl get all. All will show me replica set plus pods both instead of just watching for pods. And I just have a watch command. This watch command can be installed on Mac, on Linux. On Windows, it's possibly you can install it with Bash or let's say WSL2. So kubectl get pods or uh, kubectl apply, because it's a file that I want to apply, vote-rs. I can start by doing a dry run just to check the syntax, and dry run is equal to server client whatever it is. I like the server side dry run because it does more elaborate checks. And then when I apply, it actually will create a replica set with two replicas. That's the desired count. You can see two pods coming in, and the same pods you see launched on the right hand side, right? So that's the part with where you want to go and try this out at. So this is applying the vote, like creating a replica set with two replicas. And the job of the replica set is very simple, to give you the scalability and availability, and that's it, nothing else. How does it work? Let me show you by scaling it first. Kubectl scale, there is a scale command, there is an auto scale command. For auto scale command, you need monitoring setup, plus you need to set up the auto scaling policy, but monitoring is necessary. I'm showing you the manual scaling, meaning imperative scaling as in with the command. So I can just say kubectl scale is equal to, what am I scaling? I'm scaling a replica set. So RS or replica set, either of that will work. Replicas RS is the short name. Which replica set? Vote the name of the replica set, and then I'll define the scale. Scale is what? How many replicas you want. So I'm going from 2 to 4, and you see immediately it scales, and that's the beauty of Kubernetes scaling. It is so fast and immediate. And then I can scale to whatever I want. So I'm going to go from 4 to 8, and you will see immediately it's scaling. And I'm going to just go to 14. You see, on the bottom and on the right, you see the scale taking an effect immediately, almost immediately. And that's the beauty of Kubernetes. The scaling is very fast, and it's not just about scaling up, it's also about scaling down or scaling in. So we are going horizontal, scale out, scale in. And that's what we have here now, right? We have just scaled in. And this is about scaling. Second is availability. Kubectl get pods. And if I delete pods, you will notice two more came back up. Like, just look at the age, that will tell you how long it's been. This was from earlier. These two pods just came up, and this I can keep on doing the whole day and have fun, and it will just always come back, right? Because the replica set is watching. How does it work? Is this is part of a controller. Kubernetes has this control loop, whereas it is watching constantly for a set of whatever it, in this case a pod, and then it makes sure that the pods come up immediately, right? So as soon as it detects that, oh, there is a drift, there is a problem, there is a change, it will launch a new one. So if I delete it again, I'm deleting and doing a lot of typos in the process. Kubectl delete the pod. I'm deleting this and this pod. So see what happens. You'll also see that using the template, it picked up the name and then it added a 5-character hash to make it unique. And every time it launches a new pod, this character hash changes, this 5-character hash, to make every pod unique. That's part of a template and this replica set configuration. So if you create a pod, it is with a name that you define in the metadata. In this case, it has taken the metadata as a prefix and then added a 5-character suffix using replication controller. So when you look at a pod name, you typically know whether it was created by replica set, whether it was created by deployment, whether it was created by stateful set. So you should be able to figure that out, right? I want you to get to that level where you look at a pod name and you figure out, oh, whether it was created by stateful set. For sure you will figure out deployment, or debug set will almost probably look similar, but you will definitely find out the difference between stateful set and deployment and so on. So this is all it does basically, right? Replica set is just purely maintaining a list of pods. It doesn't know how to go from one version to another and so on. So for that you need something like deployment and so on, right? Because if I change the version, you'll see no effect really. So we look at get all with show labels. You see the version v1. Let me make some change here. There are 3 pods running with v1. Now when I change the version. I'll change it in the image and the label, both, just to reflect. Label is not mandatory, but it's good to make this change also so that it reflects in the bottom side here, output. When I apply, if it had the capability to roll out a new version, it would have done it by now. It doesn't. It just removed one because then my replica count got reset to two based on the YAML. That's what I have in the YAML. But it's not replacing the existing pods. It's not deploying a new version because it is not capable of doing that. It just does what it is asked for, that is maintaining a desired count with a specific configuration. You will actually see that replica set has picked up my configuration. That is the image. V2, but it's not rolled out. It will only do that if I ask it to launch some new ones, like I'm asking it to launch one more. So it launches with the current configuration, that is V2, but by default, it's not replacing any. If I delete one, yeah, it will. It has to launch a new one. So then it launches with a new version. But it does not have that inherent capability of replacing the pods and rolling out a new version. That is where you need the deployment. That is when we talked about, or you take the replica set, you add the update strategy, and what you get is a deployment. So when you use a deployment, it contains the replica set plus the update strategy. When it has an update strategy, and when it is a deployment, it knows what to do. It knows how to roll out, whether to have a downtime, not downtime, batch update, or recreate, like restart everything. So it knows that, but right now that capability does not exist as of this particular feature of replica set. That's why we need a deployment later. We'll talk about deployments later. But first, let's learn how to access this application and expose it to the outside world. And that's where I'm going to bring up the service, create a service. Service is like, think of it as a load balancer. You have a set of pods. On top of that, you create a service, and that service exposes your application to the outside world. How it does that depends on the service. There are like four different ways of doing that. And I have this set of pods. What I'll do is I'll create a service. So I have three pods, for example, and I'll add a service on top of that. I can scale it up later and all that. So what will happen is service will act like a load balancer, and service will also expose, or depending on what kind of service I create, it will expose my application to the outside world. So what kind of service, as in what are the types of services and how can you expose it to the outside world? Let's look at the service and the types and different ways of exposing it outside. So I can create a service of type cluster IP, which remains internal. So it will just create a IP. I mean, service gives you an endpoint inside a cluster. This is the endpoint you connect with, and then that acts like a load balancer, which connects with all the other pods. Now, when you expose it to the outside world, you have four different ways of doing that. One is you can use external IP. Second is node port. Third is load balancer. Fourth is ingress controller. Uh, Ingress controller is outside of service. Okay, there is one more way, that is host port, that is using host namespace, network namespace, and all that. So you can bypass the service altogether and expose your pod directly. That's not part of service, that's part of a pod configuration. So you can expose a particular pod on a particular port. You can do that. I mean, you can do it via service or otherwise, but that's also possible. So there are four different ways of doing it, and then there are four different types of services. Out of this, node port is a type of service. Cluster IP is type of service, but it doesn't allow you to expose outside. Load balancer is a type of service which works on cloud. This is fantastic. It actually calls Kubernetes cloud APIs. Like if you do it on cloud like AWS or GCP or Azure, the moment you set the service as load balancer, it will create a network load balancer. It's a network load balancer. It's a layer 4 network load balancer. So, but it is gonna automatically call the APIs and create it. Which one do you use typically in production like environment? Mostly it is ingress controllers. Ingress is something that you set up outside of service, on top of service, like ingress. You have Nginx or HA proxy or Ambassador or traffic. There are many. And ingress is what we typically use. We are going to look at that also. But right now, we'll just focus on how to expose this service using something simple, which is like node port. Node port, what it does is it exposes your service on all the nodes that you have on a one particular port. It's like port mapping with Docker. With Docker port mapping, what do? You have a host, you have a container, and you define a port mapping saying, oh, this 8000 port should go here. That's what we do with -p 8000 colon 80. Same thing, we take it to the next level because in Kubernetes, we don't have one node, we may have 50, and all those 50 nodes will do this. Right now, we have three. So you have a pod here running on 80, and you expose it on a particular port. There is a range for this, okay? So the range is, does anyone know the range for node port? 2. Let's say I expose it on 30,000 port. What happens is it then exposes on every single node in the cluster. That is a node port. The way it is designed is it is mainly for testing. So for developers to test it, right, quickly. This is a quick way of exposing it. And there's a range so that you exactly know that, oh, if the port is in this range, it has to be a node port. Most likely it's a node port, right? And that's why it is kind of a reserved range for that. So I will show you. This is where I'm going to say vote-svc, expose a service. So API version is v1, kind is service. This is the metadata. Spec contains type, node port. Which node port? 30,000. And then this port and target port is basically, this is the service port, right? So the 30,000 is a service port. The actual pods port is 80, and then you have something called as a service within running on every node, right? There is something, and that will have its own port as well. So you will have a listener, and then internally, if other services, let's say there is another application wants to connect to this, it will use this particular. It's a common thing. It's not per node, but it's common thing. So it has that IP and a cluster IP colon uh, port as well. So if you look at service as a load balancer, that's why I have, I think, this diagram. Service is like this, okay? You have set of pods, and then you have a service which we create as a load balancer. And then on top of that, you have a basically node port, and node port takes 30,000, right? Something like that. That sends it to, goes via the service. Service is like a load balancer. Think of it as load balancer. That service has a port and an IP, cluster IP internally. And that is what I'm talking about here, the service cluster IP. So when I create this service using vote-svcs I'm applying, see what happens in the bottom, and then we will expose, explore the service part. So it created an internal IP. This is inside the cluster. So common mistake is to take this IP, put it in the browser and think, hey, this is not working for me. Or you go and use, oh, this is a node port, so let me expose it and access it on node port, and it's not working for me. It will never work for you because this is a private IP. This is not supposed to be exposed outside. This is internal. So if you are inside the cluster, let's say from another pod, it will work. I'm on a node. I mean, this is a different setup, Linux setup. So it will work from most likely, no, it doesn't work from here either. Uh, curl might on this port. This is the internal thing, okay? And it may or may not work. No. So I'll have to create a pod. If I have another pod and I'm inside that pod, or if I get inside one of these pods and try to use, this IP, then it works, right? And then it's going to one of the containers, any of these three containers, any of these three containers, okay? And it will keep changing. So that's a load balancer by default, right? And then what happens is 30,000 is on the nodes. Which nodes? There are three nodes in the cluster. See, our nodes are containers. So this is slightly different setup, but I can do it from here. So I'm on this host where I have these containers. So I can actually do curl, and this is the first host, and on the host 30,000 port. So I can go to any host and 30,000 port basically. And then what happens is I can go to any host and 30,000 port. So instead of this, I can also go to this one. And here also I'm able to access it. That pod may not be running on that node, right? That's the beauty. That pod may not be running on that node, but if you define it as a node pod, by default, it is available on that node. So even if the pod is running on this node, you can go to this node, this node, this node, or maybe 50 other nodes, and the node pod will just directly take you to your pod or pods, and it's load balanced. Now we have, with this kind-based environment, we have done some setups. So you can go to wherever you have set up Kubernetes cluster. It could be a local host, or in my case, it's this remote server. And here I can access that application on 30,000 port. And not only that, this is already doing some load balancing. You can see that it's already doing the load balancing. So if I refresh it and check what happens here, every 2 seconds, 3 seconds, I'm refreshing. And every time I refresh, it changes between these three, which means a service by design, by default, offers me a load balancer. Now, how does this work, right? What's happening? What's going on here? If you want to understand that, let me take you to one of the nodes. In this case, the node is one of the containers actually. You can go to any of this. Container is my node, Docker. It can be your VM. It can be any of that, right? And then what's going on? Let me actually check this first. Now we're going to go really deep into IP tables and stuff like that, right? I'll tell you why also, to use a privileged. Okay, it's still the same. So how does this service networking work? You may ask, right? Because what one is, the behavior is you can go to any node, it takes you to the pod. So there has to be something which runs on every single node that is doing this load balancing. What is that thing? That's the question. Can you guess it? How about now? We're talking about how service networking is implemented internally, right? Probably you may see this for the first time ever. Most people talk about service, just different types of services, but we're going to go deeper into it. So what is it that runs on every node, which you think could be responsible for this? Because you can go to any node, you can hit any node, and it takes you to the pod, and it is doing load balancing also. So how is that happening? It's very interesting, actually. Out of these services, these pods, what we have three nodes. Can you figure out now what could be running on every node, which could be responsible for the service networking? It's not the actual thing, but it's close enough. You can see here, right? We have three nodes. So what is running with the number three here? There is one here. That's the application. Aditi says kube proxy. That's perfect. So there's kindnet, and then there is kube proxy. The whole role, the reason why kube proxy exists is this. There is a story of kube proxy actually. The story of kube proxy goes like this. Initially, kube proxy was basically a proxy. How generally the web proxies, reverse proxies are, right? And what used to happen was it runs on every node, right? It runs on every node. And then that was the proxy that your packets will go to. All the traffic will go via that proxy running on every node. And then it will decide based on the service configuration, the rules, and all that. It will then decide where to load balance and all of that, right? So it can reach out to different pods and all that. It used to be a proper proxy, user land proxy as we call it. There's a kernel namespace and then there is a kernel space user space, right? So this was a user land proxy. That user land proxy is inefficient because your packets are entering and picked up by IP tables. IP tables is part of kernel, right? So kernel is very efficient, kernel is very powerful, kernel is capable of doing the load balancing, also IP tables are. So this was moved to the IP tables later. So right now, all the load balancing and this traffic routing and everything happens via IP tables. And kube proxy still exists to update the IP table rules. I will show you exactly what I mean. I'm going to one of the nodes and then I'm showing you IP tables here. So look at what happens. So we want to traverse the path of a packet that enters our system on port 30,000. Let's just focus on this. So what happens to that packet which enters 30,000? Because that's how I'm accessing the application. How am I accessing application? I'm accessing it on port number 30,000. So what is happening with that? We'll travel with that packet and we'll figure out the connection and that packet and we'll figure out how this works. So basically, when that packet enters the system, you can go to any system and figure this out, okay? If you have access to that Linux system, you'll find out. So 30,000 is where it goes. It's picked up by IP tables, processed there, and then what happens here is what we're looking at. So IP table is made up of these chains. So let's find out what happens to the packet which enters the system on port number 30,000. It's picked up by this chain and then it says I'm going to forward it to a chain like this basically. This is the destination port, okay? And where does it go? It goes to this particular chain. So this is made up of a bunch of chains, so you can grep for that chain also, or just find out this last part and then search for it. I want to get some lines after it. After this particular string, I want to get like 10 lines after that so that I get exact rules. So I'll get minus a 10. What I want you to figure out and focus on is just this part. Yeah, I'll change the scale for simplicity. Setting the scale for, we just have replica set right now for vote. Okay, it will exactly match my presentation. So what happened was if some of you might have noticed that one line got added just now after I added that rule, right? So you now have four lines. This is what I want you to focus on. What you see here is a chain and that chain has four entries And this is where IP table is part of a kernel, and IP table is capable of load balancing. How does it do that load balancing is what I'm showing you here. It uses a simple probability model, statistical probability, and you see some number here. That probability number is what is important to understand. So 0.25, 0.33, 0.50, nothing. How do you interpret this? How do you make sense out of it? Is how many, so what is this representing really, right? We're load balancing across what? We're load balancing across a set of pods. How many pods? Four. That's why the four lines of entry. If I change it to five, let me do that. I'll change the scale to five, and you will see immediately instead of these four, and these numbers will change. Instead of 0.25, 33, 0.5, now with five pods, you have five lines here, and you see 0.20, 0.25, 0.33, 0.50. So something changed. So there is one more thing added here with a probability of 0.20. Five lines here, each if represents a pod. How do you interpret this? Is simple as this. So that's why I'm explaining this to you visually. So it goes to the chain. That chain is what we are looking at. And then when I had four replicas, there were four lines. When I change it to five, there are now five lines. And each of this has a probability number. So this is doing load balancing. How? 0.20, 25, 30, 50. So let's convert it into percentages. 20%, 25, 33, 50, and none. So what are we looking at here is if you start with 100 packets, we are looking at probabilities, okay? So if you are looking, if you send 100 packets, probability of the first pod getting it is 20, 0.20, 20%. 0.20, so 20% of 100 is 20 packets. So 20 packet, let's say, go to first pod. How many remain is the question. And that goes to the next line. And here the probability changes to 25% to adjust to that number. So that again, the 25% of it is 20. So 20 packets go here, remain 60. Out of that 0.33, 20 go here, remaining is 40. Out of that 20 go here, and then remaining go to the last line. So what this is basically representing or telling you is I am doing a load balancing across these five pods. If you send 100 packets, there's a good probability that I'll distribute it across it equally. So if you look at over a period of time, so you actually see some packets here. This you see 0, 0 because I'm not sending any traffic, or I looked at it immediately, right? I still need to send some traffic. So here I'll start sending, yeah, we are sending 20 packets a minute now. So you're going to see some numbers change here if I do it again. Something here, right? So if it is going via these services, I'm actually not hitting this particular host, I think. I have to go to, I think it's control plane or kind worker 2, worker 1. I can find out exactly which one it is. Uh, so that 30,000, where it is going, that's what we need to find out. KTS code helper. This goes back to our setup itself, since we have a kind-based environment. So 30,000 is my control plane. So I have to log into control plane. That's where the traffic is going right now. Okay, this doesn't have a name, so here I will use IP tables minus tnat minus nvl. Look at port 30,000. So that's where we begin. And then we have to go to this particular chain. It might be a different name on a different host. That's why I'm doing it again. And then I'll say, give me some 10 lines after that so that I get the exact change. And here I should start seeing some packets actually. If I'm sending some traffic and if it is hitting those that host, I start typically I see some packets here. So maybe it's a different node. I'm looking at the wrong one. That's quite possible. But the idea is the same. Probability model. That's how it is doing the load balancing. This is a simple round robin load balancing here. And that's how the kube proxy comes into play. Kube proxy is basically when you apply changes, right, to service, it goes to the master, the API server. And then from there, all the kube proxies come in and they update the IP tables basically. The role of kube proxy is there's kube proxy sideline. The name has stuck. So it still is called as kube proxy, but it is not really a proxy. It is just sitting there updating the IP tables. The actual data path is just IP tables. So whenever you change something, it gets updated, and this is how the actual load balancing happens. And that's how this traffic is being spread across. It can be handled by every node because kube proxy is running on every node, and then it can basically decide where to send the traffic based on that probability. That's the round robin algorithm for load balancing. That's the default. And that's the only thing which is possible with IP tables. There is a new thing called as IPVS, just that is also part of kernel, and you can enable that explicitly and use that as a load balancer, which is more sophisticated, supports different load algorithms for load balancing and so on. But this is how service networking works. And I just showed you one example using node port, but there are three different ways additionally you can expose your application to the outside world. One is load balancer. Load balancer needs some sort of a load balancer or some service which acts like that. Um, External IP can work with any node. You can say, I want to run it or expose it on this particular node or that particular node or two of these nodes. You can define that with external IP. And then ingress is something that we set up in addition to this. And that's what we typically use. With ingress, what happens is ingress is application layer, uh, kind of a proxy or a router, which supports many different things, including typically you will set up traffic is a lightweight ingress controller, comes with a nice UI. Also, this documentation is very good. So this is a document I typically reference. So with ingress, what you can do is eh, all the requests for different domain names like api.domain.com, domain.com/web, backoffice.domain.com, whatever it is, right? So all of these are automatically handled and routed, and based on your header, like if you're requesting api.domain.com, it will take you to a different service. If you're requesting domain.com/web, it will take you to a different service, and so on. So it will basically automatically keep on routing you to a particular uh, service, right? Service as in a set of pods in Kubernetes. And that's how ingress controllers work. That's typically what you will use uh, in most of the production infrastructure. You have some sort of a router ingress controller, and then it routes to different services. And node port is useful for quick exposing your application outside, and that's typically the use of node port. Load balancer you'll use sometimes. External IP, if you're not running on cloud, you have your own existing external load balancer. Let's say you have a Citrix load balancer or some hardware load balancer, and you are in a data center, you can use external IP to get to that also. So that's how it will work basically. So that's the service networking. And internally, when service decides that, oh, now I want to send this traffic to this particular node, it can go over in like a communication line, which sets up pod to pod communication. How does that happen, right? So we talked about this node connecting to a pod anywhere, right? When it decides that, oh, there is a load balancing and I have to send the traffic to this particular pod is on a different node. So how that is connected is where you have something called as a underlying networking is set up using CNI. So I'll quickly explain CNI and we'll stop there. If you have any question, do you have any questions so far?
Gaurav, one question on this IP tables. So
Hmm.
do we also have a flexibility to write our own firewall rules over there, or it is completely handled by Kubernetes?
It's handled by Kubernetes. The way it exposes is basically it abstracted, right? So you're
Mm.
not directly dealing with IP table. Most of
Okay.
you see, most of the
Mm.
people don't even know that there is something called as IP table which exists internally, right?
Mm.
Everything is abstracted Kubernetes. I showed you
Okay.
because just to give you a better understanding of it.
Yeah.
Now, how can you change things? It is
Mm.
possible. Let's say you can set up a specific IP
Yeah.
also, for example, right?
Mm.
How do you do that is since it is all abstracted, Kubernetes manages it. Kubernetes allows you to define that as part of a spec. That's why
Okay. Okay.
it is important to know this API reference because
Mm.
anything that you change, I'll show you one example of this. Let's look at the spec. So what is possible and what is not, you can actually check in the spec. Now we're talking about what? We're talking about services. So let's look at service here. Service has this spec. Spec contains what? These properties. So you can define uh, annotations. I think in annotations, you can define the IP specific to CNI, it will pick that up.
Mm.
You can define some traffic policies. Like you can say that uh, route to the pods on the same node, prefer that. So you can define that kind of a policy also. Internal traffic policies that local or I think that's local is or cluster byte, something like that. So the local is local or cluster. So local will route to only local pods. So you can also define that way. You can define few other configuration, but essentially the idea is if you want to change anything, it has to be done via some spec
Okay.
like this. That's why our focus in Kubernetes is figuring out what the
Yeah.
specs are, and then in the YAML we define everything.
Mm. Correct.
For example, I'll show you session affinity. Right now, it's going to any pod, right? Any of the three, four, five, whatever. So you can define a session affinity. The moment you enable that, it will be stuck with one.
Correct. Yeah.
You see right now, it's going to any, right? So it's as easy. See, it's for us, it's very easy and abstracted uh, to work with Kubernetes because of this. So what we do is, let's say I go to KTS code, projects, instavote, dev, and in service it's all part of the spec. So this is a service spec. Anywhere in the spec you can add it. So I'll just say I want to add, and everything is just here. You just have to figure out, and then whatever is available, add it as a key and value. Session affinity is what we're talking about. So session affinity, camel case, and then what is the value? We say client IP or none. None is the default. I want to change it to client IP and apply. And immediately you are going to see my pod or my from my client, this particular client, it is stuck with this pod.
Okay.
It doesn't change.
Mm.
So everything that you can be done via or should be done via in Kubernetes, the spec like this.
Right. Yeah. Sure. Thanks.
Yeah, sure. Just gonna remove this or set this to none. This is the default anyways, none is, and then it's again switching to the pods. So this is how you change things in Kubernetes. So everything is spec. That's why this is like your Bible. If you know this, and see, you can't just remember all the spec. So all you have to do is figure out like, oh, this is the property I'm looking for. Go and check the spec. That's why I say keep this as a reference. If you do that, you can do anything and everything that is possible in Kubernetes by just looking at the spec. And even if you are appearing for an exam like CKA, CKAD, the certification, this is available to you even during the exam. So you bookmark it typically and you can reference it anytime, even in the exam, because you're not expected. This is not practical to remember all the spec, right? So that's just dumb thing to do. Just mug it down. You should be able to figure out. That's more important, and that's what I like about the exam, also Kubernetes exam, where they actually give you all the resources and they give you problems to solve, and you're supposed to solve it. All right. So we were talking about CNI, the underlying networking. So how does that work? Let me give you a very brief idea about this. With CNIs are also possible. So there are three. There used to be one called as Flannel earlier, which was quite popular initial days. Then came Weave, then came Calico. I think there is one more which is quite popular these days, right? So I had a document which had some like comparison of that. I'll see if I can share it with you a little later, or let me see if I can right now. The CNI is basically, let's talk about CNI in the first place so that you understand what I'm talking about. So CNI is about uh, providing IP addresses to the pods. How do pods get IP? That's one. Secondly, how the pods talk to each other. Like if pod is running on one host, how does it communicate with the pod on the other host? That's where the CNI plugins come in. So I'll also tell you my story and contribution to that also. So CNI stands for Container Network Interface. It's a standard created by CoreOS. CoreOS got acquired by Red Hat. Red Hat is part of IBM now, but CNI spec is owned by CNCF now. They drive it, which is a good thing. When Kubernetes was created, right? Kubernetes was inspired by Borg. Borg is Google's own thing, how they run containers, and they started running containers in 2003-4. So when Borg was created, there was no software-defined networking. So what happened was, in case of Borg, they had a very complex method. So they didn't have, this is very sophisticated and good, what they have with Kubernetes, right? Borg didn't have that. With Borg, you literally had to rely on some port mapping across all the nodes, and that was very complex, not really recommended. So when Kubernetes was created in 2014 and 15, there was software defined networking already sophisticated and matured. So they had choices also between CNI and something called as CNM. So they went for CNI. CNM was created by Docker, the Docker's own standard. It's like Blu-ray versus, I think there was one more incompatible standard. For the same thing, they had two different things, right? Two different standards. Funny thing about CNM is only Docker uses it. CNI is very widely used. A lot of projects use it, including Kubernetes, including cloud platforms, including OpenShift, and many other things, right? So everyone pretty much uses CNI format. So what is CNI? CNI is a format or a language. Think of it as a language. It's a very simple language. The CNI spec, if you look at it, over like last 10 years, it has changed only, added only two words. Earlier there were, it's so simple as a language, right? Earlier there was four words. Now we have six words. And that's all CNI spec defines. That's it. If you look at the CNI spec, it takes you to this page. And how many words it has? One, two, three, four, five, six. That's it. Earlier it was add, delete, then check status. Version and GC are added later, recent like few years ago, right? Now, what is this language and what is used for? So Kubernetes defines everything as standard. It's a language. Like if you want to use any runtime, you can create your own runtime as long as it talks the same language, which is CRI, Container Runtime Interface. You can make it work with Kubernetes. Same with CNI. Any plugin that you can use today, There are many plugins. So plugins are actual implementation. Plugin is where most of the complexity is, and that's when I said I can give you a comparison between that and so on, because most of this implementation wise is all plugins. So earlier it was Flannel, then came Weave, Calico. Cilium is also, this is a eBPF. eBPF gives you some security performance advantages. So Cilium is very popular, some getting popular also now. And I personally contributed to this project called as Romana. This is back in 2013, 14, 2014, I think. That was the time when Kubernetes was like the war was heating up and containers networking basically, right? And then I had worked with someone earlier on a different project. So his company got acquired by Cisco, and then he started this project called as Romana. And we contributed mostly from the DevOps side, like automating things and benchmarking certain performance of this particular network plugin and all that. And we did some automation work for them. But that was the time when this was all getting started, really. And then Flannel became very popular. Then came Weave. Weave, the same people who created Weave, they created terminology called as GitOps, Weaveworks that is, and they went on to create FluxCD also, FluxCD, Flagger, a bunch of tools for GitOps. And GitOps wise, we have Argo also, but that's the story of Weave. And Weave was very flexible. I used to use this a lot during my trainings because it used to work very well. Calico was good, but Calico would not work on cloud earlier. That changed. Calico started becoming friendly, but I have seen some issues with Calico on certain setups and all that. We've used to work just like that because the underlying technologies where there are certain differences. Some use layer 2, some use layer 3 of the OSI model. That's where some of these differences come from. Like you have choices of technologies, and based on your infrastructure, based on certain features like network policies, whether you want to support for that or not, you pick a particular whether you want a particular security features now with eBPF and stuff. That's when you pick a particular plugin. So this document that I'm gonna share, okay, it's not. Okay, looks like this resource is not working. So it's not working anymore. That domain might have been gone, right? So it was an old document. And then if you just want to understand how something like Calico works.
How does Docker help with production quality applications? And how do you build your own Docker files from scratch? Well, if you're a software engineer interested in learning Docker,
Okay, so there's some ad playing. Okay, I'll share a video which can help you understand how Calico works, like one of the plugins. So if you understand one plugin, you'll understand how things work typically, right? With the CNI part. Why do we need CNI? Is underlying networking, and that's how your pod gets an IP. That's how pod is networked. So that part is what I'll explain very quickly, and then we'll wrap up for the day. So this is CNI. How it works is Kubernetes talks to this CNI plugins, right? And it asks this kubelet. Kubelet is running on every node. So kubelet to run a pod. And it's the kubelet which calls the CNI plugin configured on that node to go and say, hey, can you network it? Can you network this pod, right? That's why, or that's when these verbs that we talked about, add, delete, check. So kubelet will ask the CNI plugin to add this pod to a network. Okay, and that's when any of the plugin which is installed will come into play. And that's why all the hard work, all the implementation, all the complexity lies in the plugins. That's why it is important to choose the plugin. If you're using cloud, you don't have to choose it, but if you have your own data center, you typically do that. And that's where you have this language and CNI spec, and kubelet will talk to the plugin using the same language. And if you understand the language and know how to respond, you can build any plugin and make it work with Kubernetes. And that is also true with storage today. Earlier, storage was different, integrated with Kubernetes code base. Now there is a CSI, Kubernetes storage interface. So CRI is a runtime interface. CNI is the network interface. CSI is the storage interface. The Kubernetes works with these standards interfaces, and that's a very clean way of interacting with Kubernetes and building an ecosystem around it. And that's the way it has been designed. That's a really nice way, scalable way of doing it, so that anyone can bring in their own plugin or system and integrate and plug in with Kubernetes basically, or plug out with Kubernetes. That's the best part. There is always the interoperability. And the way this works is you basically have kubelet running on a node, right? And when API server says go and run this pod, not schedule, scheduling is done by scheduler. It will let kubelet know that you have to run this pod. The kubelet on that node will come in, start creating the pod. Pod is a bunch of network namespaces, and bunch of namespaces. One of this is network namespace, and then kubelet will call the CNI plugin. The CNI plugin will be asked to add the pod to the network. So it will first fetch the labels and annotations. So that's when I said, right? So you can change things from using spec. You can also add some annotations. So there are properties which are not supported in spec, but supported by certain system like CNI. A specific CNI supports certain properties. You can add it as an annotation. That annotation is read by that plugin. And then if it finds that, oh, this particular specific IP I want to configure, it will do that. And that's where annotations are useful. So it is read by CNI plugin. Then it calls the IPAM driver. IPAM driver is IP address management. So that gives the pod an IP address. And then that gets configured on the actual pod, and then the routes are set, the all the network configurations are done, and then the plugin will report back saying, oh, this pod is networked, and done, right? So that's how this pod networking happens, and that's how pod gets an IP, that's how pod gets connected to the network, that's how pods can talk to each other over the CNI plugin. And that's why CNIs are important. So, oh, the higher level networking is service level networking, load balancing, kube proxy and stuff. But underneath that, ultimately the packet needs to be delivered from a node to the pod or from a pod to the pod. That happens with the actual CNI. That's where CNI plugins and the container network comes into play. All right. Any questions here? All right. So I'm just looking at some questions on the live chat on stream as well. So that's more about how to register. So for that, we have you can visit schoolofdevelopers.com and join the mini degree program, and you can be part of the program here. That's all. There's only one question here. And apart from that, any questions on Zoom that we have people from here?
Yeah, Gaurav, I have one question.
Go ahead, Aditi.
Regarding services, and services we can add labels also and the selectors also. So what is
Correct.
the use of labels over there? Because selector I can understand it is used to select the pods,
Set
but
of pods, yes.
why we are using labels there?
Okay, that's a good question. So why do we use labels is where do the labels exist? Let's have a look at that. So labels are here. What is this label for? It's for the service. Why do we need that? I'll show you. So I have a bunch of services here. Let's say I'll look at the services all across, and I have many services. Now I want to filter a specific service. How would I do that? Is where the label is for the service. So I can filter the service using a particular label, and that label is role vote. So I can say role is equal to vote, and minus L is for filtering by labels, by the way. Okay, so it only shows me that particular service. So label is to the service, and selector is how service is sending the traffic to a specific set of pods. So how is it selecting the what we call as endpoints? Is that clear?
Okay. Yeah. And I have one more question regarding the services. So you have mentioned for node port, if three replicas are running And if we define for that replica, if we create a service which type having node port,
Hmm.
then whatever workers running, let's suppose two workers are running, so that will going to get exposed. Uh, that
Yeah.
worker IP
Hold on.
will going to get
So
exposed.
let's make it very, very simple and clear. Okay. So you're getting confused with the probably, if I understand it, you're probably getting confused with the actual pods versus the node IPs.
Yep.
So let's imagine the reason why is because our setup is like with containers inside containers and all that, right? Let's
Mm-hmm.
imagine that you have three physical servers and each of
Okay.
that has an IP, right? So let's say there are three physical servers which are part of the cluster. These make Kubernetes cluster. Let's say this physical server's IP is 10.0.1.5, 10.0.1.6, 10.0.1.7. And then inside that,
Mm-hmm.
you have set up Kubernetes cluster and all that. So there are pods running here. Each of this is a worker node, right? And now you have these pods running here. Now you expose the service, let's say service of a particular application. Now this application, there are three pods, one running here, or four pods, let's say. One running here, two running here, and one here. So these four pods belong to service X, service vote, for example, right? You created a service. Now
Mm-hmm.
it's a service of node port. What does this
Mm-hmm.
mean? Is you can access it on any node, as in this node, using the node IP. Okay, we are talking about node IP. Forget about pod IP. We don't care about that as far
Mm-hmm.
as when we want to expose it or access it from outside. We create a service. That service is translating, or if it is node port, you basically can access it as 10.0.1.5 colon 30,000 or 1.6 colon 30,000, 1.7 colon 30,000. 30,000 is generally like this. So we are talking about the node port, so node IP, and that any like let's say you hit this, right? Every time you
Mm-hmm.
refresh, you're still hitting the same node, but every time you refresh, once it goes here, once it goes here, maybe it goes here, here. That is the load balancer. So that is what I'm saying that, oh, when I'm hitting this IP, this is just one host, right? But
Mm-hmm.
that is translating to what? Translating to different pods. That is the underlying load balancing. This is where that IP tables and everything that I showed you comes in.
Okay, if we hit the IP of the
Node,
first node, then it can hit the second or third also. I thought,
pod.
yeah.
Exactly.
Okay,
That's
okay.
what I said. So
Mm,
how is it possible for this node to find out is basically that IP table we saw, right? IP table and this
mm, mm,
probability and all that. So list of pods.
mm-hmm.
So those are pods across cluster. And
Okay.
how, when, let's say, decided to hit the pod, let's say this is pod A, B,
Mm,
C,
mm,
D. Let's say it is trying to connect to D. How does that happen is where you have CNI. This is where you may have, this node, this node, this node, all of these nodes connected via some CNI. And let's say we
mhm.
have Calico here, or in our case, what is the CNI? There's KindNet or something. So that CNI is what we have. So basically, you will see some pods running for that. That CNI is implemented using KindNet. So you have something running here, some pod, especially here, 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 that is setting up the CNI. So when this basically says I want to connect to D, it is actually the path is via this CNI network, and then it will originate here, then it will go here. That's why I explained the CNI, because that CNI has provided the IP address in the first place, and that CNI has provided this link, whereas you can connect from node to pod or from pod to pod again via the same CNI.
Okay. Yeah, got it. So Gaurav, we can't use the same port for different service because now this port
Absolutely.
is reserved for this particular service.
And that is reserved across the nodes.
across the nodes.
Exactly. So if you try to create another service with the same node port, you will have a problem. It will not work. So that's absolutely correct.
And that is not the case with cluster IP.
Yes, cluster IP is like a virtual thing. Cluster IP is unique for every service. Every service is going to get its cluster IP, right? And then
Mhm.
each of this IP is unique. This is internal to the cluster, and there you can have cluster IP colon port and whatnot and all that. So every service will anyways get its own IP there.
Okay. Yeah, got it. And last question. You
Okay.
mentioned ingress controller.
Correct.
So at the end, ingress controller is of type load balancer only. Service type
No.
is of.
The
Uh,
difference is how it works, so at what level, and so on, right? So, are you familiar with AWS Cloud, for example?
yeah.
Okay. So, there are two types of load balancer in AWS. One is you may have heard of. So, which load balancer have you heard of or used?
Nginx I have used.
No, no, but AWS has this managed service, right? Some
Mhm.
ELB, LB, NLB. So,
I
no
have
problem.
not
So,
used.
So in AWS, you have two types of load balancer, and this is common. I gave example of AWS is because if you know, it's easy to relate with. So there
Mm-hmm.
are two load balancer. One is ALB, second is NLB. What is the difference, right? So difference is this acts at a layer 4, that is a
Oh.
transport layer,
Mm-hmm.
which is where you have TCP UDP. This is at the layer of L7. L7 is application layer. And we are talking about practically we use TCP IP. Theoretically, it's OSI model.
Mm-hmm.
So the difference is basically between this and this. So this is at the transport level, network load balancer, and the application layer is where your L7 is. Since it is at application level, it is more intelligent because it's an application, right? It's not just a transport protocol, which is TCP or IP, UDP. In case of load balancer service type, it always creates a service of type uh, network load balancer. So even in cloud, you have that clear differentiation that this is a network load balancer, this is your application load balancer. If you have application load balancer, then you can do this, not with network load balancer, right? Like routing, for example. It can look at your header because it's an application. So it can keep track of a header. Based on that, it can do some routing. So that edge proxy or reverse proxy or router is possible with layer 7, and then it can do more things like rate limiting. It can do load balancing algorithms can be decided at the application level. Nginx supports it. Traffic shifting, traffic routing, when you use canaries, like 20% traffic goes to this service, uh, 80%
Mm-hmm.
goes to the previous service or new service. So you can define all of this if you have a layer 7. Plus with layer 7, what happens is with ingress is layer 7. So traffic itself, this is actually an example of ingress controller traffic, but it can be replaced with nginx also. Nginx can be made to work as ingress controller. What is the difference between a plain vanilla nginx and ingress controller is basically when it becomes an ingress controller, it is same nginx, but on top of that there is a wrapper which talks to Kubernetes, and it is capable of looking at your ingress rules. Like in Kubernetes, you'll write a YAML code saying that, oh, this rule, like api.domain.com, send it to this service. So that is a rule. You can define it as YAML. I'll show you how that will look like. And when you define a rule like this, so ingress controller is nothing but you have the actual in nginx, for example, and then ingress controller is like a code sitting on top of that, like a bot sitting on top, and then it allows you to write some rule like this. For example, you can say, oh, if rule is if web.example.com send it to a service whose name is x on port y, like service port 80 or whatever. So if you define this rule, that bot is capable of basically updating nginx automatically. That is what makes it an ingress controller, nothing else. It's very simple. So you just take the same Nginx, add this wrapper, which is listening to your rules. If you add a rules, it immediately updates Nginx self-update. So you don't need a ops person to go and add a rule and all that. That intelligence is built in. That's what makes a application like Nginx an Nginx ingress controller. That's all it is. And then the features of Nginx come in as layer 7 ingress controller. So it becomes more like ingress versus layer 4 is more like a typical TCP IP load, UDP level load balancer. And that doesn't have that much intelligence. It gives you better performance, but ultimately it's a layer 4. So typically, since for microservices, you have more applications, you may need some of these features, but you typically need a router like Nginx, and that's where you use ingress controller uh, as some sort of an ingress controller. It can be Nginx, it can be traffic, it can be anything really. That's where it
Okay.
comes. That's why we put that's why I put this as a separate red link, because this is layer 7, which is
Mm-hmm.
ingress. And then load balancer can work with NLB. And then all of these are layer 4 actually. Node port, external IP, load balancer, except for layer 7, where you actually set up something on top of your existing service.
Okay. Mm. Got it. Thank you.
Sure. Any other questions, folks? All right, if not, we will wrap up here. So that's it for this week, for this masterclass. What you should do is go through this lab guide, go through the course that we have or a recording of this, and then go through the lab guide. And there is more to what I've explained in the lab guide also and in the course also. So where this is the deep dive that I've already shown you, like how the services work under the hood with IP tables. All these commands that I tried are here. The only thing is, instead of the entire thing, you just pick this part and grep for it. That is better. But otherwise, you can see that statistic uh, algorithm of how a probability model, how the load balancing happens. You can try exposing services with external IP. This is not very useful for kind-based environment. That's why I don't show you. But if you have it on VMs or otherwise, you can actually see it. Internal service discovery is also useful. That's for connecting one application to another, like this vote application, when it wants to connect with backend service like Redis. How does that happen? That's a name-based service discovery. So you can check that as well. And that's how you connect this application to another. Here you just need cluster IP. So for these three services, if we had three services like these internally, these only need cluster IP. You don't have to think about how do you expose it, all these options that we mentioned, because who is going to connect to these is just internal applications like vote and result. So not every service needs to be exposed outside. So for all of these, cluster IP. Only for external facing applications, voting result in this case, you have to think about how do I expose, and that's where everything that we talked about comes into play, including node port, ingress, load balancer, external IP. That's all. Right, so that's it for today, and that's all for this week. I'll see you on Thursday when we have our office hours session. This time I'm going to talk about Argo CD. So I'm going to do a live session. I'm going to try that as a live session on multiple channels, most likely. So I'll send out, so it will not happen on Zoom, but I'll send out a link for the live stream, and you can join in live and post questions for sure. And it will be a complete demo of Argo CD pipeline. So CI and CD with Argo workflow, events, Argo rollouts, and Argo, uh, let's say, CD. That's it, right? So entire CI/CD pipeline I'll demonstrate with that. That's what I have in the plan. So that will be very interesting for you to understand how to set up a Kubernetes native CI/CD using GitOps tools and a set of Argo tools, basically. That's it for today. Thank you, and I'll see you next week in the next masterclass, where we'll be talking about deployments, storage, and possibly config maps and secrets. Until then, thank you, and you have a great day and great week ahead. Bye bye. Aditi, you have a question?
Yeah, Gaurav, I have last one more question.
Go
In
ahead.
load balancer, like for cluster IP, it can be behind Nginx. So can we do the same thing for our load balancer also? If some service is defined as a load balancer, uh, then can we put Nginx uh, like before it or after it?
So what does it mean? So cluster IP is internal IP inside the cluster. I understand
So
that. So your question that you want to put in ingress controller itself on a internal IP?
no, no. Like whenever the traffic is coming, so like in our current setup, first it goes to Nginx and then like it goes to all the services
Services, correct.
which are defined as a cluster IP. Okay. So
Correct.
I have like one requirement in which the service will be load balancer. So load balancer type.
Okay.
I just want to know whether can we put a load balancer also behind the internet?
See, you most likely wouldn't do that, right? So if you want to put it behind Nginx, the question is why to even use load balancer as a service type? Why not use just the ingress controller? Is there a specific need?
Yeah, so the deployments which are running on a different clusters,
Okay.
they have different capabilities. There are few sessions attached to them.
Sure.
And like they have some cache uh, like all the deployments are not same although the code is same but like whatever the streams getting created whatever clients are getting attached to it
Mm-hmm.
so these deployments are they are forwarding some traffic from one pod to another, from one
Mm-hmm.
cluster to another.
One
So they
cluster
are
to another.
different.
Okay.
Yeah. So they are all different. Like when we use Nginx, we when we use Nginx to route the traffic, it can go any cluster. But
Correct.
here when we are using the load balancer, we are exposing it as load balancer because it hits the first cluster. If that
Correct.
request is not successful, then it will try for the second one. If it is successful, then it will get connected to that second one only.
Mm-hmm. So you want to set up a load balancer which spans across different clusters? Is that what you're trying to do?
Yes,
Okay. And is it on a cloud?
yeah,
Which kind of a cloud?
AWS.
AWS. And are we talking about like network load balancer or is it application load balancer?
It is application load balancer.
Okay, so are you saying that in this, but it's in the same region, I assume, right? So same AWS region.
Uh, but in prod, cluster will be in different region also.
So you have different regions. So if
Yeah.
you have different regions, typically, I mean, see, the ALBs don't span across regions. What you may have is possibly, let's say this is a region. You can see my screen, right?
No, no, I can't see it.
Okay,
Yeah.
let me share it again. So let's say there are different regions, right? So typically in my, say, load balancers don't span across. So you can't have a load balancer which will span across like this, right? It won't happen. It may be different availability zones, which is part of the same region, and that's fine. But if you're talking about different regions, definitely there has to be, I mean, some load balancer here, some load balancer here. On top of that, typically you have Route 53 or something similar, which is doing health checks, and then this will fail over. So if this is not working, it will fail over and so on. So maybe it is a DNS level load balancing, and then it can go here. But uh, I don't
DNS load
think,
balancing.
yeah, DNS
They
load
have
balancing is possible.
they have different subdomains.
No, no, same domain. points to, let's say, xyz.com. It can
Mm-hmm.
have two DNS servers, two DN IPs or CNAMEs. So one is pointing here, one is pointing here. Same domain, huh? Same domain is can resolve to different regions, different IPs also. So Route 53 is capable, since it integrates with AWS, it is
Mm-hmm.
capable of doing this health checks and saying or distribution. So you can either use this as primary and failover, or you can have both live. This is live, and spreading the request across it. So there are different design patterns, and
Mm-hmm.
based on that, you may want to figure out how this will work. So coming back to your question about whether we can make ingress point to a load balancer service, I think
Mm-hmm.
that is possible. Because, see, ultimately, a load balancer service is exposing your cluster IP plus load balancer. So it will have a cluster IP plus it
Mm-hmm.
will have a load balancer IP. So when you use ingress, so
Mm-hmm.
ingress, what happens is ingress doesn't send it. Ingress doesn't send via load balancer, but ingress will typically, based on the service, it fetches the endpoints. And ingress is the one which is doing the load balancing direct to the pod. So it doesn't go via this, it will go directly to the pod. So it is not really, I mean, you are just exposing a load balancer service and then also going it via ingress. But if you start using ingress, in my opinion, it will take this route and
Mm-hmm.
directly go to the pods, because that's what it does with a typical cluster IP service also.
Okay, it won't use load balancer. It will
For the
directly.
traffic, I don't believe we can look into that deeper, but I
Mm-hmm.
don't believe that it will use load balancer.
Okay, okay. And if we are using direct LBIPs, like let's suppose for LBIPs we have done some DNS mapping and
Mhm.
using that, then it won't use ingress at all. It will directly hit the pods.
Yeah, yeah. That is a direct load balancer, no? Then you are just going via the load balancer, and
Mm-hmm.
then it will land up to that is using the load balancer as service type.
Okay. Yeah. Actually, I was thinking about putting behind ingress what will be the cons and like should it,
To
like is
me,
it a better design or not?
design wise, either I would pick, if I have to design it, either I will pick load balancer or I will pick ingress controller.
Okay.
Because see,
Okay.
what you're trying to do is just redundant here, because you're saying that if I use ALB, ingress
Mm-hmm.
itself is equivalent of ALB, or you can actually use ALB as an ingress. That you can do. ALB is a kind of an ingress controller also. So you can integrate that as an ingress controller and say, instead of load balancer, there are two things, right? One is
Mm-hmm.
load balancer as service type. That is layer 4. That will create
Okay.
a network load balancer.
Yes.
And you can integrate ALB, which is a layer 7 load balancer, and that works as ingress controller also. So that is probably what you may be looking for.
Mm-hmm.
So here you don't
Okay.
need two things, right? So just one thing
Mm-hmm.
which acts like a load, kind of a ALB, load application load balancer already, and that is the ingress controller which is sending to the target group or the pods through that.
Oh, okay. Mm.
Yeah, makes
Oh,
sense.
yeah, yeah, makes sense.
All
Thank
right,
you.
but you can go back and think about it, and then if you have further questions,
Mm.
we can talk about it in the next sessions also.
Sure.
Yeah.
Thank you.
All right. Sure. All the best.